In this class, we are going to consider the mathematical representation of a wave motion. And at the end of this class, we are going to treat the following definition of a progressive wave. Every progressive wave must have a frequency, wavelength, and period. We are going to consider all of that, and then we are going to solve some mathematical problems on this topic. Let's proceed. Looking at this figure gives us a clearer picture of what a progressive wave is all about. So you can see how the wave progresses from the point of origin. This wave has period, amplitude, wavelength. A progressive wave is a wave that spreads away from a source, transferring energy from one point to another. We are going to look at the definition of all the terms, the summary, before we go into the mathematical aspect of it. I read what is here. A progressive wave is one that moves from place to place, transferring energy without the transfer of matter. So a wave that moves from place to place, from one point to another, transferring energy without the transfer of matter, is called a progressive wave. The next definition here says that the displacement of a particle on a wave is the distance in a specific direction from its position. The distance in a specific direction from its position. So if we go back to the above figure here, and then on this figure, the displacement moves in this direction. Okay, so this is where you have the x direction. You now see that's the direction of the displacement of the wave. Another term we have to know about is the amplitude. Of course, the amplitude of a wave is the maximum displacement of the particle. The maximum displacement of the particle. Looking at this figure here, you see where we have the maximum displacement of the particle. That gives us the amplitude of that wave. So if I'm asked to mark the amplitude, I will mark it at this point. You now see that the crest of this wave has a maximum displacement. So we will consider this as the amplitude, the point where we have maximum displacement of the wave. Let's now move down to another definition. The wavelength is the shortest distance between two peaks, or the shortest distance between two troughs. It can also be defined as the distance moved by the wavefront during one oscillation of the source of the wave. So whenever we are talking about the wavelength, it's simply the distance between two successive crests or trough. If we come back to this figure here, considering this figure, you now see that we have a crest at this point. We have a trough at this point. So the distance between this successive crest and trough gives us a wavelength. I have to write that very well. So at this point here, we have wavelength. Okay. We can also draw another point for the wavelength over here. From here to here is another wavelength and all of that. So the distance between two successive crests or trough of a wave gives us the wavelength. Let's move down to the next definition. The period of the wave is the time for a particle in the wave to complete one vibration or cycle. So the period of a wave is the time taken for the wave to make one complete oscillation. The time taken for the wave to make one complete oscillation. We can't talk about period without the frequency. The frequency is the number of complete cycles a wave makes in 1 second. The number of complete cycles that a wave makes in 1 second. When the crest and trough of two waves are aligned, the wave is said to be in phase. These are terms when it comes to waves. So a wave can be considered to be in phase when the crest or trough of that wave has aligned. Okay, the crest and trough are not aligned. If the crest and trough are not aligned, then the wave is said to be in phase difference. When the crest and trough of two waves are aligned, the wave are said to be in antiphase. When the crest and trough of two waves are aligned, the wave is said to be in antiphase. The difference in distance traveled by two waves is called path difference. The difference in distance traveled by two waves is called path difference. Okay, so we are going to look at the mathematical representation of a wave. Look at the mathematical expression here. Y equals to a sine 2 pi x over lambda. The A there represents the amplitude of the wave, and the x represents the displacement of that wave. We have discussed this in the figure above. Then the lambda represents the wavelength of that particular wave. So if we have a wave as the one that we have considered above, that is about to move, a progressive wave, we have equation 1 represents a progressive wave. So this is a mathematical expression for a progressive wave. Assuming the wave now moves to a particular point in space, then we are going to introduce the velocity and time. You will see that in equation 2. So let's continue. The y here signifies the vertical displacement of the vibrating particle. Vertical displacement of the vibrating particle. The x is the wavelength, lambda is the wavelength of the wave, and amplitude of the wave is capital A. The horizontal coordinate, we have the horizontal displacement of the wave is taken as x. So the m or the A here represents the amplitude, and the unit is in meters, m. The wavelength also has the SI unit in meters. But if at all a problem is given, the unit would also be specified. In this case, we can see a figure below. On this figure, the maximum displacement of the wave is given. So one can just consider the maximum displacement of this wave to be 2 or plus or minus 2 centimeters according to the figure. So you can see the maximum displacement of this particle is given. It's very clear as well. Okay, so we can also draw the line for the wavelength of this very particular wave and all of that. So this is an example of a progressive wave, and the nature here is this is a sine wave, a wave that is progressing from a particular point. Equation 1 gives the displacement of any particle at a distance x from the origin. The displacement of the particle after some seconds is given by y equals to a sine 2 pi over lambda into x minus vt. This expression is not different from the first expression. The only difference is that if we have a particle that moves away from the point of origin, we have introduced the quantities v and t. So the particle now has velocity and time. Assuming that there is no time or velocity is 0, this equation 2 will reduce back to equation 1. I don't know if you can see what assuming I substitute 0 into this place where we have v. If I put 0 here, you will now see that this equation reduces back to what it was initially. That's what I'm trying to say. So if we have a progressive wave that is moving to a point P, and that wave has velocity and time, then we will always consider this equation, which is equation 2. So I have already said the meaning of v and t. So the v there means velocity of the wave, and the t represents the time of the propagation of that wave in seconds. So if we clear the bracket or expand the bracket, looking at this equation 2, we want to expand the bracket. That means that we are going to use the equation outside the bracket to multiply by the one inside the bracket. So this one will be multiplied by this, and this one would be multiplied by this. So 2 pi over lambda would be used to multiply by x, and 2 pi over lambda would be used to multiply by vt. When we do the multiplication, we now have the next expression, which I'm going to write down. Okay. So you now see y equals to a sine 2 pi x over lambda minus 2 pi vt all over lambda. Initially, we had 2 pi outside here, so when you expand the bracket, we get equation 3. Equation 3 is not different from equation 2. Now, looking at this equation 3, look at this point. You will see v and wavelength. What does that mean? Frequency. V and wavelength means frequency. I will explain that. Looking at this one means wave number. I will explain that as we continue. Remember that V equals to F lambda. V is the velocity of the wave, F is the frequency, and lambda is the wavelength. If we make the frequency the subject of the formula, then we will get V over F. Now, the V over F you are seeing here represents frequency. So we are going to replace that expression V over lambda with F. So this expression will now reduce to y equals to a sine 2 pi x all over lambda minus 2 pi ft. Equation 4. Still the same equation as equation 2, still the same equation as equation 3, but I'm trying to break it down so that you understand that all these expressions are the same things. You don't have to cram it, you just understand how it works. Remember that 2 pi f equals to angular velocity, 2 pi f, angular velocity. So it will not be wrong if we replace angular velocity into equation 4 where we have 2 pi f. So at this point here, where we have 2 pi f, we are going to replace the value for the angular velocity. When we do that, we will obtain the next expression, which is equation 5. You now see how they are all related. So equation 6 shows that y equals to a sine into kx minus omega t. So look at this point here, 2 pi all over lambda is the same thing as k. 2 pi over lambda is the same thing as k. So in place of 2 pi over lambda, we substitute the wave number k. Let's consider this example 1. Example says, a plane progressive wave is represented by the equation y equals to 2 sine into 2000 pi t minus 0.5x, where the symbols have usual meaning. We have explained the meaning of those symbols there. So the first option here now says, what is I, the frequency of the wave, II, the period, III, the amplitude, IV, the wavelength, and V, the velocity of the wave. For us to be able to solve this problem, we are going to consider the 6 expressions that we have written above, the 6 equations we have listed above. They are all the same. So all we need to do is to compare equation 1 to 6 with the equation here when we compare them, we now strike out the common terms. This is what I mean. By comparison, the equation is given y equals to 2 sine 2000 pi t minus 0.5x, according to the first example. So we now check from the first equation 1 to 6, which one is similar to what we have here. I would be comfortable considering or picking equation 6. I can expand it later. If you look at this equation, I think it's similar or almost similar to equation or the expression that was given in the equation. So I just come here and write it in a way that it will align with what we have here. Look at it carefully. At this point, we have even seen that if I compare this here, you see the value of the amplitude, so A equals to 2 here. The sine will cancel out the sine, y will cancel out y. I will also compare this. I compare this and cancel out the common terms. And then I will now figure out what I'm looking for. I will also compare this, cancel out the common terms, and figure out what I'm looking for. It's very easy. Let's go to the first option, frequency. We are to find the frequency of the wave. So here we have frequency in this very expression. I'm going to compare it with the one that is above. I will compare this one and this one. So we'll now have 2 pi ft equals to 2 pi ft equals to 2000 pi t. Pi ft equals to 2000 pi t. Looking at that, what is common? What is common to both sides? You see pi here, pi is here, and pi is over there. So this one here will cancel this. T is here, and t is there. So this one will cancel this other one. So what is left would be 2 pi equals to, 2f equals to 2000. 2f equals to 2000. So our next expression would be written as 2f equals to 2000. Dividing through by 2, the coefficient of x, so we can make f the subject of the formula. When you do that, okay, 2000 divided by 2, we get 1000 hertz. So we have been able to solve for the frequency. We now go back. The next one was period. Remember that frequency, f equals to 1 over t, is inversely proportional to the period, and period is also inversely proportional to the frequency. So if we are to find a period, we just divide it by the value of the frequency. That's 1 over frequency gives us the period. So t equals to 1 over f. 1 over 1000. You get 10 to the power minus 3 seconds. The next one, the amplitude of the wave. Looking at this expression, we can see clearly that where we have A corresponds to where we have 2, so there is nothing to calculate here. We already see that the amplitude of the wave is equal to 2. So let's go ahead. A equals to 2 meters. The next one, the wavelength. Okay, so for us to obtain the wavelength of the wave, we have to compare this other side of the equation. Have to compare this other side of the equation. Why I said so is that if you can recall the list of the equations we wrote down, you will remember that K equals to 2 pi all over lambda. Okay, so we already have K here to be 0.5. And if pi is given, then we would always be able to solve for the wavelength. That's what we are going to do now. So Kx equals to 0.5x. By comparison, comparing this side of the equation, Kx equals to 0.5x. Can you see that? So we now have Kx equals to 0.5x. Of course, x is common, so it will cancel out. And the K here means 2 pi over lambda. So we will now have that K equals to 0.5. So we now have 2 pi over lambda equals to 0.5. If we make lambda the subject of the expression, looking at this clearly, if I make lambda the subject of the expression, I will have lambda equals to 2 pi divided by 0.5. So if I divide this by 0.5, I will get 4 pi. The unit should be in meters. That's what I'm going to do now. Okay, so we now get 4 pi in meters. 4 pi in meters. If we substitute the value of pi, assuming pi is given, we now substitute the value of pi into that expression, it will give us the real value of the wavelength. But in this case, it's still correct. Wavelength equals to 4 pi. The next question said, or the next option said the velocity. The velocity. Remember that V equals to F lambda. We can still use this expression rather than making comparison. If we make comparison, we still get the same value. We already have our wavelength here to be 4 4 pi. So this is our wavelength, 4 pi. And the frequency is also given. We have frequency in the equation to be 1000 hertz. Look at it here, 1000 hertz. So we are going to multiply the frequency by the value of the wavelength. When we do that, we now have 1000 times 4 pi. 1000 times 4 pi, we get 4000 pi. Velocity is in meters per second. So please, I would like you to encourage our channel by sharing our videos, recommending it to your friends, and also clicking on the subscription button if you are yet to do that. Thank you, I would really appreciate that. Let's check the next example. Example 2. Example 2 says, a plane progressive wave is y equals to 4 sine 100 pi t minus 50 pi x. Estimate the following: amplitude, frequency, period, wavelength, and velocity. We are still going to compare as before. So we are going to write the given expression, the given mathematical expression, and then we go and check equation 1 and 6, which one corresponds to this. I will still take that equation 6. Then we now compare. By comparing, even before I consider the equation, I have seen that the amplitude here is 2. I also see, compare this, and then I cancel x. If I cancel x, I will now see that k equals to 50 pi. If I compare this as well, I cancel t. Since it is common, we now see that angular velocity omega equals to 1000 pi. Okay, so let's now move to, let's consider the first option. I, amplitude. The amplitude of this wave equals to 4. Not just 4, but 4 meters. Then the next one is frequency. For us to get the frequency, we are going to compare the left-hand side of this equation, this other side. So we have angular t equals to 100 pi t. Angular t equals to 100 pi t, because this will cancel out. So if we do that, what would be the next step? Okay, so look at this. Angular velocity times t equals to 100 pi t. The angular velocity is 2 pi ft. So with this, we are going to derive the value for the frequency. Take note that t is common, so t will cancel out. Pi is common, pi will cancel out. This is what I mean. This one will cancel this. This one will cancel this. So what would be left is 2f equals to 100. When we divide 100 by 2, we obtain 50 hertz or per second. So if you don't call it hertz, you call it per second. The next option said the period. Period is inversely proportional to frequency. So t equals to 1 over f. We get 1 over 50 seconds. The next one says wavelength. For us to get the wavelength, we still have to make comparison. But this time we are going to compare this side of the expression. Remember that k is equal to 2 pi all over lambda. So when we do that, we will now deduce the wavelength from that very expression. Kx equals to 50 pi x. By comparison, 2 pi x over lambda equals to 50 pi x. We cancel out the common terms. This will cancel this. This will cancel this. When we do that, we now make lambda the subject. Okay, so 2 over 50 is 1 over 25 meters. So the wavelength is 1 over 25 meters. So the last one is velocity. Just as the first example we solved. Remember this expression for velocity of a progressive wave. V equals to f lambda. Even if I make comparison, I would still get or obtain the same expression. So here we have lambda to be 1 over 25. Can you see that? Then the wavelength or the frequency, the frequency is here, 50 hertz. Okay, so when I substitute the value of the frequency into f and the value of the wavelength into lambda, I get 50 times 1 over 25. Of course, this will cancel out. Looking at this, 25 goes here 1, 25 goes here 2. So V equals to 2 meters per second. Thank you for watching our video today. I would like you to recommend us to a friend. If you are yet to subscribe to this channel, please endeavor to do so. I really appreciate your stay. Thank you and have a wonderful day. Bye.